Okay, so I'll just start with a quick introduction while a few people join, and just to give you a background to what's going on. At any point, I mean, please ask questions at any point in the course. That's the point about the course. I'll reiterate that. I should get in chat, or we can do. You should be able to turn your video on and talk, or if it's a one-on-one, we could do a breakout session. But I'll just get going for the moment. So. This course is given as part of the ARCHER2 service, which is the relatively new UK national supercomputer service managed by the research councils, but housed, operated, and supported by us, EPCC. I'll say what EPCC is very briefly in case you don't know. And the hardware, actually, I say hardware supplied by Cray. That's slightly old-fashioned. It's HPE now. HPE bought Cray, so it's now an HP machine. I should update that. Training. So as part of that support service, we provide training through the Computational Science and Engineering CSE support team, and we do 60 days per year at various locations, of course, mostly online at the moment, although we are moving back towards face-to-face training, and it's free to all academics. This is the this is an artist's impression of the machine, the ARCHER2 service. I mean, this course isn't about ARCHER2, it's about advanced MPI, but it's done as part of the ARCHER2 services, and we will be using ARCHER2 for the exercises. This is a picture of the machine as it is installed just now. This was actually an intermediate machine, but I quite like the picture because you can see the back. You can see all the very complicated networking you have on these systems to connect them up. We have other systems at the ACF, but they're not relevant for this. The ACF is the Advanced Computing Facility, just 10 kilometers south of Edinburgh, which EPCC, where we house all our machines. So what is EPCC? Well, it's the closest thing the UK has to a national supercomputer centre. We were founded in 1990. We're technically called EPCC, but originally the Edinburgh Parallel Computing Centre. We're a centre at the University of Edinburgh, and we've been running national parallel systems almost 20 years now, since the Cray T3D, coincidentally a Cray machine back in '94. There's over 100 of us, and we do a range of academic and research and commercial projects, and a lot of teaching and HPC training. And again, get in contact if you want. You might come away from this course and say it'd be nice to collaborate with EPCC in the future. In terms of collaboration, at least with academics, EPCC staff are just like standard research associates. So a lot of EPCC staff are named on other people's research grants as postdocs, effectively. Or research projects. A European project consortium is more difficult now, obviously, with the UK's status in the EU, but we have historically done a lot of European projects. This isn't a face-to-face course. I thought I'd show you a picture of Edinburgh. If it was a face-to-face course, you might be in Edinburgh. It's a very nice city. These are the ARCHER2 resources. You won't need them, hopefully, because hopefully this course will be self-contained. But I just thought I'd put them up there. Who am I? My name is David Henty. I'm in charge of education and training at EPCC. I run the on-campus MSc. We have a praise training centre. I do, like this, courses in the ARCHER2 training programme. But my research interests have kind of been parallel programming models, accelerators, performance, parallel I/O, things like that. Please fill in the feedback form. You'll be sent an inquiry at the end. If you have any general inquiries, they go to the support email. We run a one-year taught postgraduate master's course, which you might be interested, some of your colleagues might be interested in, since 2001. There's a picture of a recent graduates, and just plugging our own course here. It's available on campus, or we also have a fully online version now. This is the class. I think this is 2014 class, quite a long time ago. We also developed a supercomputing MOOC, a massively open online course with funding from Prace, that originally ran in a facilitated mode, where we had tutors online to answer questions, but it's been in a self-study mode now. So I mean, you'll know this material yourselves already, but some of your colleagues might be interested. They wanted to learn about the basics. It's entirely conceptual. There's no programming involved. It's all about the concepts. During the course, you'll have personal accounts for the duration of the course. We'll allow machine access for about up to a month afterwards, just so you can practice the exercises. Shortly after the access ends, the files and stuff will be deleted. So take copies of any work you have. Take copies home. Don't worry about the course materials. all the course materials will continue to be available from the ARCHER2 website going forward. Longer term, there's a lot of ways to apply to time on ARCHER2. All of them, it requires some justification of resources. You know, you need to justify your access. Often people apply as part of a larger grant. Pump priming has the lowest barrier to entry, that's to get going. Or you can take the ARCHER2 driving test, where you would get 800 compute units and 800 node hours for up to 12 months if you wanted to play around with stuff. And that's a way of getting on the machine just to test things out. Again, security of the room isn't relevant for these face-to-face courses. But just generally, you know, people come from a wide range of different backgrounds in terms of their experience and such like. So just generally, be polite to people. I'm sure you all will be. And if there are any issues, then there should be a form on that page. The regular funding calls, we fund, as part of the service, we fund RSEs, research software engineers, to develop software for the service. Again, that's you can see there, ECSE, the ECSE program it's called. You can see information there. Just very briefly what the hardware is. I said this isn't a course about ARCHER2, but ARCHER2 is quite a large system, over 6,000 nodes, 750,000 CPU cores, fairly standard access via Slurm for SBatch and SQ. Again, this should all be set up for the exercises. Just very, you know, you have the main thing which gets people, and hopefully I've put this on the instructions. There are two file systems, and when you log in, you'll end up in your home file system, but you need to work in your work file system. You need to cd/work, and it's, of course, it's TA073 for you guys. /work/TA073/TA073/username. If you don't have, you will be able to do the exercises on ARCHER2 using any account, but we have a dedicated course queue to get you rapid turnaround for a course account. If you haven't applied for a training account yet, you can apply. Claire will have sent you the instructions. It only takes a few minutes to set up the account. And this course is part of PRACE, which is a long-running European program. Just very briefly, there's 26 members. The UK has been represented by EPCC for a long time in PRACE. And as part of that, PRACE set up 10 training centres, PRACE training centres, and this course is being done under that umbrella. There's a whole bunch of them there all over Europe, and they'll all have their own training programme. And if you want to look at all the training courses which are available, there's a central website, training.praceri.eu, which you can look at. So as I said, you'll get us. So I hope you enjoy the course, and please do ask questions. That's the point of the course. I'll explain. I said text is often easiest, chat, I mean, or audio. It's really up to you. So what I'll just show you is the setup for the course. So I'll just stop sharing. And if I look, sure. So now, apologies, I'm on a brand new machine. I've only, my previous laptop exploded, bust, and so I'm on a new machine as of about the past week. I'm used to Linux, and this is a Windows machine. So apologies if things are not as seamless as they ought to be. It's because I am using a machine I'm not familiar with. So hopefully you can see, yeah. You can see, so for the materials for the course, ARCHER2 website, just go to training, and we have advanced message passing programming here. You see it's part of the PRACE program. We have our general timetable here, which I'll try and stick to, but there's also course materials here, and this is just a GitHub page, but hopefully I wouldn't bother about the stuff here. Hopefully I put in a reasonably decent README, which also has the timetable and links to the lectures and the exercise material and instructions and such like. So hopefully you can all see that. The reason GitHub is weird about links. It's strange. So if you go to these, yeah. Anyway, I would recommend you use these links here because these will actually give you the actual material. So I just wanted to do a very quick. So you'll see here that there's a quiz. Okay. So I was going to set up I was going to, if people could go to that, I will set, if people could go to that link there, this MPI quiz, and I'll see a student login, and the room name is HPC quiz, and then you join. But I've got to log in as an instructor, so I'll basically do that now. But if people could go to that MPI quiz, I've got just an initial getting to know you quiz, which I was going to set up, and it'd be good if people could go there. It'll take a second for me to get this set up. Apologies. Again, this new machine is somewhat defeating me. Okay. So so you should see, can people confirm they can see it? I've just got a little survey to find out who people are. So there's only about 4, if people could log on to the, so what's happening? Too many windows open here. So the room name is, it should say, so it's an MPI quiz, room name is HPC quiz. It should be on the screen there. Yeah. So what I will do, so we've got half a dozen people on. If people could join that quiz, that would be really good. So I said, just log on to that MPI quiz. Room name is HPC quiz. Give me a sec now on that. So still a few people haven't joined us. Wait a bit. We've got 6 or 7. Okay, so I'll show the results, and we've got, okay, one in Scotland, England, and outside UK, but in Europe. Okay, fine. I'll do that. Just interested in what people's position is. So, oh, MSc, PhD, okay, fine, that's interesting. Thank you. Next question is, so MPI is neutral between C and 4 channel, but I wanted to know what kind of, what language people were likely to program in, and whether they were, trying to encapsulate the different styles of programming. You can call MPI from Python, but it's I mean, I have some experience with that, but it's not. I mean, it's there, but it's not what you would do on a large scale. Most large scale applications are written in C, C++, or Fortran. Okay, let's have a look at the results. Okay, so a range of, okay, so one's admitting to being old style Fortran 77. Okay, that's, so I in general, the exercises are doable in C and Fortran. Some of the examples I'll give out just for you to run. One is only in C, I think one is only in Fortran, but that's just as the instructions and things assume. For me, for the instructions from my side assume that you're doing C or Fortran, really. But C++ is fine. It's just that MPI is a C library, so you have to call it. If you program in C++, you just have to call it MPI C library. Okay. Just interesting what systems people use. Just to get some feeling for people's experience. So we have, okay, ARCHER2. Okay, that's interesting. So just interested in people's coding work, just to get some idea of what people. Any more people want to just put there? Okay, so yeah, so a lot of, I know people know a lot of people work with existing MPI codes. That's interesting, thank you. And I just wanted to, I'll leave this up for a bit, but I just wanted to get an idea for what people wanted to learn from the course. This is anonymous. I should have said this is all anonymous. So I'd be interested if people, I'll leave that up for a bit. So one of the things I do at the end of my, I'll leave that up for a bit. So I'm just putting it in a chat. So at the end of my introductory MPI course, I have a quiz mainly on MPI basis and point-to-point communication. Some of you may have done that, but I'm interested in whether people would want to, are interested in it'll take about half, 25 to 25. So I'm just wondering if you, whoops, do a quick poll. So you should see a poll come up. Can people see that the polls can be? They've recently changed the interface to this system as of yesterday. So again, that's a double whammy for me. I'm on a new computer using a new system. But so you should see. Okay, I've seen some. I mean, one of the reasons. Okay, so it looks like it's actually not maybe a few, but so I think it is worth doing. As I think one of the main things I like to start, even though it's an advanced course, is that it does get us talking about some aspects of MPI which are worth thinking about. So we're just maybe 5 minutes behind, but we can catch. So what I'll do is I will finish that. That did something stupid there. Okay, so I need to okay, fine. So I will take a screenshot of this if I can get my. Okay, so I have a screenshot of that now. Thank you. So I will now start a different quiz. So okay, this question is really just there to check that the quizzing system works. We already have that little survey, so that's fine. But there is something. This does have a point to it. Anyone else want to take a guess? So the main point is that there are some of the questions have more than one answer. So not all of them, but some of them. So MPI is both the message passing interface, but also a way of doing distributed memory parallel programming. So although A was the obvious answer here, there are more. Some of the questions have more than one answer. So that was just that. Okay, that's. So so I should say before I carry on, none of the this is anonymous, so just guess if just guess if you don't know, because I'm interested in what people think. None of these questions are stupid. In fact, for almost all these questions, all the answers are perfectly reasonable answers. For if I said to you we're going to do message passing programming on ARCHER2, that could have required special compiler, special library, special parallel computer, a special operating system. All those are possible answers. However, this is a quiz about MPI. And for MPI, some of these answers are true and some of them aren't. But as I said, don't worry if you're not getting them right, because these are not trivial. They may seem quite straightforward, but they're not trivial questions. And none of the answers are stupid other than the first question. They're all perfectly sensible answers. It's just a question of MPI for MPI. What is the right answer? So anyone want to guess? So I'm just having a slight, oops, what am I doing? I'm on the wrong, no, I'm on the wrong window here, sorry. There we go. So, okay, so yeah, so it requires special libraries such as the MPI library. Again, special compilers is not it's a perfectly reasonable answer because MPI purports to give you special compilers. You do MPI-CC, MPI-F90, MPI-CXX, but of course in MPI they are just wrappers which set up all the include paths and the whatever, the link paths and all the random stuff you don't want to care about. So although MPI makes it look like it has special compilers, it does not. You're just using GNU, Intel, or the Cray compilers depending on what you want. So that's worth remembering. And the reason I put that up is it means that MPI will give you almost no help. Sorry, your compiler will give you almost no help. Okay. I've started an MPI program. I've written an MPI program called my MPI program. I do MPI run -n for my MPI program. What does the and then within that program, of course, I will have a call to MPI init. What does that call do? And again, if you don't know the answer, please just guess or put down what you think is the most plausible, because again, all these are perfectly possible answers, but it's just interesting to know, what MPI does rather than a generic. I keep saying generic message passing system. I mean, we'll see this. There is only one message passing system people use now, which is MPI, but MPI has made various choices about these things. If anyone wants to, anyone else have a guess? Okay. So most people got it right. So it doesn't create the 4 parallel processes. Again, there have been message passing systems in the past where that was true, but in MPI, so in some older message passing systems, can someone just confirm they can you see my camera? Again, I don't see the same view as you. Are you seeing my camera? I mean, at least in some sense, can you see my? Yeah, fine. Okay. So in some message passing systems, you ran a program and then you ran a special function which created multiple processes. But that's not what happens with MPI. In MPI, you write one program, but the 4 programs are launched by MPI run creates 4 multiple copies of a program, and it's at the launch stage, this magic MPI run program, which actually creates the parallel processes, and all the MPI init does is it makes them talk to each other. So interesting question. If you call MPI receive and there's no incoming message, what happens? Again, when there was more than one message passing system, there were different choices from different systems. Okay, so show results. Oh, well done. Okay, so receive and await. That's okay. Well done. That's so. I mean, you would think there would be a timeout. I mean, you think if you've got a receive there for like 10 hours, why isn't it timeout? But as I said, MPI is not fault tolerant. So if you had a message passing system which was fault tolerant and could cope with dodgy hardware, you would have timeouts on things. But MPI assumes that your program is 100% correct and that the hardware and software is 100% reliable. And so for that reason, it assumes you've written a correct program. But I think the reason I asked this question is to show that MPI is not fault tolerant. This is not the behavior you would have for a fault tolerant system. These are getting a bit more technical. So if you call MPI synchronous send and there's no receive posted, which of the following are possible outcomes? I say possible outcomes. These won't necessarily happen, but again, the reason I ask a lot of these questions, there were things that people used to misunderstand, and on my introductory course, I slightly teach to these questions now. So if you've done my MPI course recently, you'll be a bit of an advantage, because I kind of maybe spend too much time talking about these issues, but they are important. Okay. So yes, it's synchronous. The send waits until the receiver is posted. So well done. So synchronous is like making a phone call. So people have got good knowledge. So that's very good. Next one, if you've got MPI asynchronous send. Now I don't really, on my course, I don't really talk about buffered send, other than to tell you to not really use it. But a buffered send is asynchronous. The analogy is synchronous send is like making a phone call. Buffered send is like sending an email. That's kind of. But buffered send is a bit weird. So which of these are possible outcomes? Okay, not defined, but as I said, if you don't know, just take a guess, because I said they're all perfectly sensible potential outcomes. But I'd be interested in what people think from your experience of MPI. You may never have used buffered send. It's not widely used for reasons which I hopefully will be explained here. Okay. So someone said, see, that's actually what synchronous send does. So buffered send is like sending an email. It's just fire and forget. So that means that D and E are the sort of the message stored and delivered later on if possible, and F, the sending process continues execution regardless of whether the message is received. That's however, B is a possible outcome, and so when I originally wrote this question, I didn't have P as a possible outcome. Someone pointed out it is. So anyone could hazard a guess in the chat. Why could a buffered send fail? You tell MPI, I've got a message. I want you to send it asynchronously, which means it has to take a copy of it. That's what the buffered means. So MPI takes a copy of it, sticks it away in its back pocket, comes back to you, and then later on will send that message. Yes, the buffer is full, exactly. And the strange thing about MPI is that it is up to the user to provide that buffer space. There's a horrible routine called MPI buffer attach, where you say to MPI, here's 10 megabytes of storage, which I've allocated. I'm going to give it over to you to do buffered sends. So Philippe is absolutely right. MPI bsend can fail because the buffer can be full. So you may never have used MPI bsend or ssend. What most people use is MPI send. Okay, so there's the obvious question now. If you call standard send and there's no matching receive, which of the following are possible outcomes? And again, this is probably the most misunderstood, well, actually, one of the most complex and commonly misunderstood parts of MPI. MPI send is your go-to routine for sending a message. Okay, what it actually does is slightly strange. You might not, it may be not what you expect. Definitely isn't what I expected when I first doing MPI programming. But I was lucky because at the time that I learned MPI, there were people at EPCC developing MPI libraries, so I could just go and ask them. But it's not obvious from the documentation or even from experience what MPI send actually does. Okay, so we've got a good. So let's see. Anyone else want to take a guess? So, so the message doesn't disappear. MPI. There's only one routine which you should never use called MPI rsend ready send, where a message will disappear. MPI is sort of written to be correct. So they're very good. So so the point about MPI send is MPI send is written specifically so that MPI can decide whether to use synchronous or asynchronous communications, and it's undefined, not specified whether MPI send is synchronous or asynchronous. So you would think that the correct answers to these questions would be the answers to question 5 and question 6 added together. And that's true for CD. If MPI decides that MPI send should be asynchronous, then D and F are true. The message is stored and delivered later on, and the program continues execution. If MPI decides that it will be synchronous, then it does C. However, so I'll come back to that, Michael. That's a good question. However, why A was a positive? So if you tell MPI you have to do a buffered send, you have to take a copy of this message, it can fail because there's not enough buffer space. However, if you tell MPI, could you do standard send, MPI send, and you decide if it's buffered or synchronous, then the send will never fail with an error. Why is that, do you think? It's not, but again, this is slightly. The point is that MPI has its own internal buffering reserved, 10K bytes, something like that, which it will try and buffer messages in. So what MPI send tries to do is it tries to take a copy of the message, return to you, and carry on. However, if there's not enough buffer space, rather than failing with an error, which is what MPI send would do, it says, well, there's not enough buffer space, so I can't buffer it, so I will become synchronous. So MPI explicitly decides, in practice, decides that small messages are buffered because it has buffer space, and large messages are not buffered, and it becomes synchronous. It waits for the receive to be posted. Now, Michael asked that this be a written program. No, because that only happens when MPI decides to buffer the message, and so it has taken a copy into an internal buffer. So does that make sense? So the important point is whenever a send routine returns to you, that's a blocking one, a standard one, it is safe to overwrite the send buffer, because either the message has been delivered if it were synchronous, or it has been copied into an internal buffer if it were buffered. But in both those cases, it's then subsequently safe to overwrite the send buffer. Does that answer your question, Michael? I don't know if that's quite what you meant. Yeah. So the next one is when you do a receive, it's MPI receive buffer count data type source tag communicator, if I remember correctly. Status at the end. The MPI receive routine has a parameter count. What does the count mean? Again, this isn't entirely. This is far from obvious. So this is one of the unfortunate things about MPI. The two routines which you use most, MPI send and MPI receive. MPI send is more complicated than you might imagine, and MPI receive is also slightly, maybe not quite what you'd think it does. I mean, maybe you guys know. I don't know. Anyone else want to take a guess? Okay, so so it's good people spot it's not bytes. So MPI really doesn't like talking about bytes. When you start talking about bytes, I know C programmers love talking about bytes. When you talk about bytes, you've got a non-portable program. However, technically, now in many programs, B is true. Okay? In many programs, it will be the size of the incoming message. Okay, so if you're doing a standard 2D halo swapping code, you know that if your halo is 8 integers, then what your neighbor will send you is 8 integers. So you do often, but technically that's not true. Technically, when you issue a receive, what you're saying to MPI is, I would like to receive a message, and by the way, I have enough space, say 10. I have enough space for a message of length 10. That might be the size of the incoming message, but it's not necessarily the size of the incoming message. Technically, it's the size of the buffer you have received. The size of the buffer you have allocated to receive the message, which may or may not be the same as the. So clearly, the obvious, what happens if the incoming message is larger than count? So you do an MPI receive, and you say, I'm going to receive integers, and count is 10, and then the incoming message is 20 integers. What happens there? You just want to have a guess? It's not obvious at all, but okay. So what happens here is MPI receives with an error, fails with an error. MPI tries to be kind of safe. So MPI doesn't write beyond the end of the available storage because it's trying to be safe. The reason that you tell it how big your receive buffer is to prevent that from being. D is an interesting answer. The problem with D is that so if you're from a background where you think of communications as happening through pipes, you know, a pipe model where you push data in one end and it comes out the other, you would say D was the right answer. You said I want to receive count items, okay, and so you receive count items, okay. However, I've got this example where imagine I'm sending 20 integers and you receive 10 of them. What would happen to the remaining 10 integers? Well, do you have to issue another receive? The reason why D isn't true is that in MPI, it's very much based on matching send and receive. So one send has to match one receive. So you can't issue one send and have it received by two receives. That would be true if you had a kind of a pipe model where you just push data in one end, a streaming model, and pulled it out the other. But MPI is based on the idea of discrete messages, which are either received or not received. So why it's not D, I think, is that, you know, what would happen to the unreceived data? And okay, the next question is the obvious one. What happens if the incoming message of size n is smaller than count? Do MPI receive and say, I've got a buffer of size 10 integers, and then the incoming message is only 5 long? What happens there? Okay. So so MPI is written, again, it's not obvious. You may never have actually done this, but MPI is written to allow you to receive messages of unknown. There are situations where you might not know how big the incoming message is, and MPI wants to let you cope with that. So what actually happens is the first n items are received. So most people got that right. Actually, it doesn't receive with an error because MPI is designed to allow you can receive messages of unknown size. The reason the rest of the storage isn't zeroed, I can think of two reasons why that isn't the case. One is you can imagine you might have data in the buffer you don't want to be overwritten. I think the main reason, though, is performance. I mean, if I did an MPI receive and my receive buffer was a gigabyte long and I received a byte, what's the point in zeroing the other 999,999,999 bytes? That will take a long time. So I suspect it's just for efficiency that that D isn't the case. So it's actually C. So okay, fine. So I've issued an MPI receive with count equals 10 integers, and that receive has returned to me. All I technically know is that I have received a message of 10 integers or less. Now, in many of the programs you've written, you may know that it's 10 integers because all your messages are 10 integers. But of course, in general, all you know is that a message of size 10 or less has been received, 10 or fewer. But clearly, if it's fewer than 10, you need to know how many there are, because you need to know which of the values in the receive buffer are now are valid. So how is the actual size of the incoming message reported? Anyone else want a quick guess? So, okay, so you're right, MPI can tell you, and it's stored in the status parameter. The value of count could be updated. If you're a Fortran program, that would seem reasonable. But if you look at the C prototype, you'll see that it actually is passed as a by value, not by reference. So yes, the status, got that right, is so when you do an MPI receive, you specify two pieces of storage, the receive buffer, where the data goes in, but there's also metadata associated with the message. And so you specify somewhere to receive the metadata. And in MPI, that's this magic thing called the status. For technical reasons, the count isn't stored directly in the status. You have to pass the status to a routine it's called MPI get count. It's a bit nasty, but that's the principle. So the other questions here, I think I wasn't going to go through because they're not really relevant for this. This is the only one I wanted to do. Apologies for the formatting here, and if you're a Fortran programmer, but hopefully this is just for fun, really. I'm just checking. I've done something a bit weird here. Fine. So I've got a piece of code here. If you're a Fortran programmer, all you need to know is that the even processes go into this. The even process do an MPI roll reduce of their rank. So we're adding up ranks. Okay. So what is the output of this MPI? Got an 8 processes, i.e. running on ranks 0 to 7. The even processes do MPI on reduce of rank. So they're adding up their rank and storing it in even sum, and it's one integer, and they're adding it with an MPI sum. And the odd processes do an MPI on reduce of their rank, and they put into odd sum, which is one integer. So we're all adding up our ranks, but the even processes store it in even sum, and the odd processes store it in odd sum. So what do people think the output of that? This is quite a tricky one. Well, potentially tricky. And if you don't know, just take a quick guess. So you know, 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 is 28. 0 plus 2 plus 4 plus 6 is 12, and 1 plus 3 plus 5 plus 7 is 18. 16, sorry. I said if you don't know, just have a guess. This is probably the. Just wait a second and then. Okay. So the question is written to make it look like the answer is C, even sum equals 12, not sum equals 16. But actually the answer is B. Can someone tell me why the answer is B for those of you that copy? This is the closest thing I have to a trick question. So you know, it is something of a trick question. But why is the answer B? I don't want to type it into the chat. Hopefully you can all see the chat window. What's the critical, the crucial point? Anyone want to type it in? Or so I got a beep there, but send copy. Yes, sorry. Fine. So absolutely. So This is where this code is deliberately written to be misleading, but the important point is they're all calling and a reduce on com world. And you might think it's, so in fact, that reduce, where are we? That reduce on rank 0 matches this reduce on rank 1 because they're in the same communicator, MPI com world. And you might think, well, how can two reduces on different lines match each other? Well, you should ask the opposite question. MPI is a library. MPI has no idea where you've called the reduce from. All that rank 0 knows, for example, is that, okay, I've been called to do an MPI on reduce on com world. Okay, that's all I know. So I'm going to wait for everyone else in com world, which is all the other processes, to call an on reduce. I don't care. And in fact, I don't even know what line in the, now in most normal programs, all processes are calling an all reduce from the same line. But actually there's no restriction in that. All that the MPI library knows is that it's expecting everybody to call it. And so that so that they match. And that is that is a function of it being a library. Because it's a library, it cannot know where it was called from. So you get, this is deliberately written to be this misleading. Apologies for that. So okay, I hope that was useful to go through some of the basics. Well, I wouldn't say basics, some of the corner cases or the commonly misunderstood parts of the basic MPI. I'll stop sharing now if I can work out how to do that. So what I was going to do next, if I go to the timetable, is I'll go through. So what we'll do is we'll take a 5-minute break, and I'll start lecturing again at 10. This is quite a short, relatively short lecture, so we should stay back on time. But just unfortunately, we don't have other than those quizzes, we don't have a practical exercise in this first session, so it's a bit lecture heavy. But I'll take a 5-minute break. I'll be back. I'll start lecturing again at 10:30 with the next. So I'll just fine. So it's. I'm sure it's a sign of old age like me that people are interested in the history of things, but it is definitely worth looking at the history of MPI, how it came about, and I think it's MPI is completely dominant, the dominant way of programming large-scale parallel computers today. That wasn't an obvious situation 30 years ago when MPI was developed, so it's kind of interesting to look at what's happened. So, oops. So I'll do a very brief history of the MPI standard. What was the situation before MPI, MPI1, MPI2? I think actually this is actually MPI4 is here now. This is slightly, I haven't updated this correctly. And before, this is a good time to be doing parallel programming, because before MPI, so that's in the late 80s, early 90s, there were so message passing was an established way of programming parallel computers, but most vendors had their own libraries. So when you bought a new computer, you had to rewrite your code in the new library, and that was annoying. There were some portable libraries, but typically they're developed by academic groups for research purposes. They might have targeted a particular system or interconnect and only optimized for a very small subset of the platforms. And also different libraries use different models of communication. So for example, all those questions I asked, like what happens if you issue a receive and there's no send? What happens if you issue a send and no receive? It would have varied from library to library. So for example, there was a library called PVM, Parallel Virtual Machine, which was designed with clusters of workstations in mind, which is clearly then you have to worry about fault tolerance because somebody could come in and switch their workstation off. So in PVM had timeouts, and you could do health checks. You could ask, is processor 7 still alive and things like that. But MPI was an attempt to define a standard set of communication calls. And the reason why MPI has been successful, at least one reason, is that there's been a lot of work done previously. And so to some extent, MPI was just the best of breed. Some sense MPI is too big. There's too much stuff in it because they put everything into it. But in some sense, also, they didn't put everything into it, but they were able to. People had tried message passing in various ways and worked out probably what the best way to do it was. The MPI forum was set up. Vendors and academic library developers were represented. This is one of the reasons why the specification is so large. Lots of different models of communication, synchronous, asynchronous. But the important point that vendors and library developers were present, because of course, if you're a library developer or sort of a user, you want to have it as much as possible. But if you're the vendor who has to write and support this thing, you want it to be as small as possible. So there's some tension there. And a lot of the library developers wanted things. For example, one of the main things about MPI is there's a lot of scope for optimized versions on different hardware. That was thought in from the very start. We will try and specify things at a high level so that at a low level you can implement things in different ways. So many aspects of the specification are deliberately vague or not specified to allow different implementations to work in different ways. Like, is MPI send synchronous or asynchronous? You don't know. So this makes it easy to port or optimize for new hardware, but you need to be aware of this when writing code. So it said erroneous applications. You may write an incorrect code, but it happens to work on one MPI implementation but fail on another, and that's a classic. You may assume that MPI send is always asynchronous, at least for certain message sizes, and that may not be true. As we know, MPI is an API, application programming interface. It's not a piece of code, it's specification. So the MPI manual, MPI defines what the functions do. But since 1992, so basically MPI1 was finished in 94, and it had all the features of MPI that you probably an enormous number of programs written today would still effectively written using MPI as it were, defined back in the early to mid 90s. There really wasn't much done, so there were just various bug fixes but then in version 2 in 1997, they did two things, well, a number of things that they put off from the first version, which were parallel I/O, which I don't cover in this course, but is actually still alive and kicking and works very well. Remote memory access was a way of doing direct read and write. It's called put and get. So that's sending data to a process when there's no receive, and receiving data from a process when there's no send. I will cover various aspects of that tomorrow, but the way it was defined back in 97 wasn't particularly successful. C++ was integrated. Dynamic processes is something which I've almost never seen used. When you launch an MPI program, there is a way to shrink or grow the size of the communicator. So you could say, well, I started on 8 processes, but now I'd like to run on 24. Could you please give me an extra 16 processes? However, that really is very rarely used. It really doesn't fit into the MPI model. And in particular, it doesn't fit into the way that supercomputers are managed. When you run on the supercomputer, you submit to a batch system. The batch system gives you 1,024 CPUs for 5 hours, and you either use them or you don't. You can't ask for more. If you don't use them, they go wasted. So it's that dynamic process, which was a fundamental feature of some other MPI, some other message passing libraries like PVM, is not really commonly used. So MPI was stable for about 10 years, but then a big change happened in the mid to late 2000s, that machines started to get a lot bigger, and we also had shared memory nodes, and those two aren't unconnected. One of the reasons that MPI was designed where people thought you'd never really run on more than 1,000 processes, but from the 2000s onwards, we started to get machines with many thousands of processes and with multi-core nodes. And as we've seen, ARCHER2 has 6,000 nodes, each with 128 processors on it. So this was then, and then there's various fixes and clarifications, small updates. Something called neighbourhood collectors were added, which I don't really cover here, but I can if you're interested. This unified RMA model is what I'm going to cover. This is this remote memory access, direct read and write. How it was defined back in the 90s wasn't particularly successful. And there's been more recent development, and most recently version 4 was released a year ago. It has something called persistent collectives, which again I can talk about, but I don't cover in any detail. So I mean, I've talked about MPI+2 and subsequent versions have something called one-sided communication, where in normal message passing, send and receive, the data transmission and the synchronization are the same thing. You issue a receive, you wait for the send to come in. But in single-sided, all the parameters are specified by a single process. So what you can do is I want to write data to that process's memory, which is called a put, or I want to receive data from that process's memory. And this introduced the concept of things called windows, a chunk of local memory that will be accessed by remote processes. So I talk about this in more detail tomorrow, so I'll defer to going into any detail here. But there are certain situations when I think this is useful and others when I don't think it's useful. And I'll cover what I believe are the useful situation tomorrow. I'll talk about that tomorrow. MPI3 brought in a lot of things, non-blocking collectives. You'll see send have blocking and non-blocking versions. Send when you call MPI send, when it returns the send is completed. Or let's think about receive. When you call receive, when the receive returns, the receive has completed, data has been received. As we've seen that the receive will wait for a message to come in, so we have the problems of deadlock. So non-blocking is a way of saying, I'd like to issue a receive, but just sometime in the future, I will receive some data, but return control to me, and I'll carry on doing something else. So non-blocking, I'll carry on in the background. So they introduced non-blocking collectives like all reduced were previously only blocking, and also these neighborhood collectives. They improved the one-sided communications, and they added a new tools interface and a new Fortran bindings for 2004 and 2008. The new Fortran bindings are very nice. They basically just replicate the C interface in Fortran. When MPI was defined back in the early 90s, Fortran was pretty primitive, didn't have derived types. It's still Fortran 77 really. But when Fortran 90 and more modern versions of Fortran came in, you have a very nice interface. Not many people use it, I have to say. I don't see many Fortran programmers using it, and maybe it's historical. Other new features, some various, these are just very much little technicalities. And the important thing, I think, was that C++ language bindings were removed. C++, there used to be a separate C++ interface for MPI, where I'm not a C++ programmer, so apologies if my terminology is not correct, but the MPI functions like send and receive were methods on the object, and the object was the communicator. You did com.send, com.receive. However, C++ was developing and expanding at such a massive rate that they decided that it just didn't have enough effort to support that. And so you can call MPI from C, but MPI is a C interface, and so you have to understand how this, and that's the interface between C++ and C is well defined. Therefore, the interface between C++ and MPI is well defined, but it's not an object-oriented library. There were changes to collectives. Non-blocking versions were introduced. IB counts, IR reduce, IR. These are just like if you call it MPI all reduce, when the routine returns, the all reduce has happened. When you call an MPI IR reduce, which is the immediate version, the non-blocking version, it just initializes that all reduce, and you get back a request, a ticket, a handle, so you can later say, could you please tell me whether that is completed or not. They return an MPI request like these other non-blocking functions. For technical reasons, well, I don't find these non-blocking collectives particularly useful. I've rarely come across a case when they have been useful for people in terms of performance, at least. We can come back to that. And neighborhood collectives were introduced. So an MPI all gather is a routine which collects data from everybody. You gather from everybody. An MPI neighbor all gather, note the American spelling, gathers from your neighbors. Well, what does your neighbors mean? Well, it assumes you've created a virtual topology. And the ones which I cover in my introductory course are Cartesian communicators. What you tell MPI when you create a virtual topology, you tell MPI, actually, I've got 16 processes. They're actually arranged in a 3D grid, a 4x2x2x2, a 4x2x2 grid, for example. So MPI then knows your processes are in a 3D grid. So when you do an MPI neighbor or gather, it doesn't gather from everybody, it gathers from all its neighbors, which are its 6 nearest neighbors in a 3D grid. So this is a routine which is really useful for nearest neighbor stencil-based computations. And in fact, you can do halo swapping in a 3D regular grid with a single MPI call now, if you're brave. I'm just going through the changes. There were changes to one-sided, and what the slightly bizarre thing about the single-sided is that you could access the windows, which were logically shared memory segments, but you had to use function calls, put and get, to read and write to those memory locations. So even if you were accessing data on a process which was on the same node as you, in the same shared memory computer, you had to use puts and gets. MPI+3 introduced a new unified memory model which allowed you to basically create shared arrays like you would in OpenMP, and just to read and write directly to them. So all the processes on a node can actually share data with shared arrays with it in the new MPI model. And that's the model I'm going to cover tomorrow, because I think it's the most useful one and the one which gives you most benefit. This is called the unified memory model, so I'll talk about that tomorrow. We also have persistent collectives. Again, what you do, one of the weird things about MPI is that when you call a reduction, you might call an all reduce 1,000 times, 1,000,000 times in a program, and every single time it might have the same parameters, the same input and output buffers, the same communicator. All those things might be the same. But each time you call it, MPI has to assume that the parameters could be different. There's no way to tell MPI previously, look, I'm going to do this collective call. I'm going to do it thousands of times. That's what persistent collectives are. You tell MPI, look, I'm going to do this collective call, maybe an all reduce, and I'm going to do it millions of times. So MPI can go away and work out the most efficient way to do that, knowing that the time it's spent on that investigation of the most efficient method will be recouped because you're calling the routine millions of times. And so persistent collectives are potentially very, very useful. Fault tolerance was proposed. It's always been proposed. Everyone always goes on about fault tolerance, but it did not appear in the 4.0 standard. Again, I don't think fault tolerance will ever appear in MPI. I think it's not. I mean, I don't think it's particularly useful. Which, if you come from kind of a pure computer science background, will seem madness. But if you're an applied computational scientist or data scientist, I think that for large parallel supercomputers, MPI is not a fault-tolerant model. If you're going to do grid computing or cloud computing, you would not use MPI. You would use a different interface. So I think putting fault tolerance in MPI post hoc is not going to be successful. So that's talk about just before implementations. There are many different implementations of the MPI specification. For example, the C language is a language specification, but you could use the GNU compiler, the Intel compiler, the Cray compiler, the Windows compiler. So there were many different there are different implementations of the MPI specification. Many of the early ones were based on pre-existing portable libraries. People took their portable library and put an MPI interface on top. But there really are two main open source MPI implementations now, which are called MPI-CH and OpenMPI. And if you're programming on your laptop, you're probably using OpenMPI. That's the one which is most easily bundled up with Ubuntu, for example. But if you're using ARCHER2, for example, and other systems, it's often based on MPI. Intel have their own MPI as well, which isn't open source. But many of the vendor implementations are now based on these open source versions. So, I mean, this is quite an old slide, but there was a lot of early research. EPCC had a message passing library called CHIMP, and they produced a CHIMP MPI. Before MPI, we had things like CHIMP, LAM, PVM, parallel virtual machine, P4 macros. But these P4 sort of developed, well, there was also EPCC developed MPI for the early Cray machines, but that wasn't continued, at least in production. So really, Argonne National Lab had this project called MPI+, and that has become MPI+2, which is now called MPI+, and that is where the Cray MPIs come from, and probably many of the MPIs you might use on clusters. The people who developed LAM and PVM at different Ohio and Oak Ridge went through various implementations. Now they convert an OpenMPI. So MPI+CH and OpenMPI are the two major libraries at the moment. MPI+CH is virtually the default implementation. It's very mature, and many vendor MPIs are based on it. It's been through a bit of history, but it was called MPI+CH, then MPI+CH2, but it's now back to MPI+CH again. And it uses a standard model. You know, what you want is you want to be able to be portable to different hardware. How do you do that? Well, you have an abstract model. You have a layer which specifies how you do the very low level operations, which is say sending and receiving raw bytes. So in MPI+CH, this is called an ADI, the abstract device interface. And so basically, if you want to, most of the library is portable, and at the lowest level, it calls these low-level routines, which it calls an ADI, an abstract device interface, to say I want to send 16 bytes from process 1 to process 7, and to port to a new machine or to a new interconnect, you just have to re-implement those functions. So porting the library to a new interconnect is relatively straightforward. These will have default implementations as well, but you can override them to be more efficient. You won't be doing this. This is what a library developer does. OpenMPI was, I think, relatively new. It's been around for a long time. It was a joint product. It was basically initially focused very much on fault tolerance, but that's probably not such a big deal now. But also a big emphasis on InfiniBand hardware, which is very common now. And it's open source with a very large, and it says community effort. So I have OpenMPI on my laptop. OpenMPI was a terrible name. We'll see tomorrow that there's also this shared memory thread-based parallel model called OpenMP, which has been around since the 90s. OpenMPI was developed after that, and people get very confused between OpenMP and OpenMPI. OpenMP and OpenMPI are totally different things. OpenMP is a compiler-based mechanism for threads-based parallel programming, and we'll look at tomorrow how to merge MPI and OpenMP. OpenMPI is an open source implementation of the MPI library. They shouldn't have called it OpenMPI. It caused a lot. I don't think it caused a lot of problems. So the summary is, most MPI implementations use a common superstructure. There's most of the code is dealing with a range of MPI issues which are not hardware specific. You know, looking at data types, communicators, argument checking, and stuff, things like that. And there'll be a lot of different ways, protocols of sending data. We'll talk about it later. You might ask, how does MPI actually send the data? Well, we'll talk about that in the next lecture. But the hardware-specific code is separated away, and in MPI+CH, that's through this thing called an abstract device interface. So to optimize for a particular architecture, you rewrite the low-level communication routines in the ADI. Again, some modern networks are very clever, and so some modern networks can do things in hardware. For example, some modern networks can do an all reduce, can add up data in hardware. You can just you can say to the network, here's a number, could you add it up across the network? So you don't have to, you can optimize the collectives. So you might say, well, I can also optimize MPI all reduce, because on this InfiniBand hardware, there's some low-level routine which does that. So that's why MPI is successful. It's very high level, and the MPI library will automatically use machine-specific capabilities when they're advantageous, because you hope that the library developers have optimized it in that way. Again, MPI was developed in the days when a computer had a single process. Now all computers have multiple processes. Okay, we have modern MPI libraries. Modern MPI libraries are aware of shared memory nodes. So, for example, we'll see this when we do the exercise after the next lecture, that sending data between two processes on the same node within the same computer is faster than sending data between two nodes, because MPI notices that and uses a different way of sending the message. And so it is rare nowadays that you have to worry about. So MPI library includes, although MPI's high-level model doesn't talk about nodes, it talks about processes. A high-level MPI doesn't talk about how the processes are mapped to physical processors and physical nodes. The library has their optimizations to speed up the node local operations, as I said, like send and receive within a single node. So the ADI, the abstract device interface, will have multiple implementations. There'll be a way of sending bytes between processes on the same node, which will hopefully use shared memory, and bytes between processes on different nodes, which will use the network. So that's really a summary, a brief history. I'm back on time actually. I'll go back and look at the timetable. Let's just check where we are. I'm just trying to find my apologies. I do apologize. I'm not 100% au fait with this computer. There we go. So just to kind of map out the rest of the day, we're going to talk about point-to-point performance and do a practical after the coffee break when we go for lunch. Then after lunch, we'll do MPI optimizations. I'll talk about how to use MPI, how to use the basic routines like send and receive, but use them efficiently. And then we'll have a coffee break. In the final lecture, we'll talk about advanced use of collectives. So that's what we're going to talk about today. Tomorrow, the whole of tomorrow is really focused on how do you take advantage of the fact that modern computers have shared memory nodes, and there's two ways of doing that. One is to combine MPI and OpenMP, so use OpenMP for the parallelism on a node, just like you would on your laptop, but MPI for the parallelism between nodes over the network, and that will be the morning. And then in the afternoon, I'll talk about that has its advantages and disadvantages. The main disadvantage is you're using two parallel models in the same program. You have to know MPI and OpenMP. However, there are ways to take advantage of the shared memory nature of modern computers using pure MPI. That's this RMA, remote memory access model. And I will talk about that in the afternoon again with a practical. And for example, just to kind of to think ahead, one of the main things that may have occurred to you is on a machine like ARCHER2. Imagine you've written an MPI program where each MPI process has a large lookup table, a very large static lookup table. In standard MPI, each node of ARCHER2 will have 128 copies of that same lookup table. Each process will have its own copy of the lookup table, which seems crazy. This both methods, but this in pure MPI allows you to have a single copy of that lookup table per node, which saves you a factor of 128 in memory, and that can be quite important on modern machines. So that is something which, if you're, and it can also allow you to do more optimal communication and give you some more benefits there. So that's the layout of the day. We're going to have to take a break now, have a coffee, and come back and talk about point to point. And I'll give a lecture, then I'll have a practical. We can look at these issues and run on ARCHER2. If anyone is having any problems logging on to ARCHER2, we can sort them out during the practical session. So I haven't given the exact timetable here, but I suspect most of these sessions, which are down for an hour and a half, will be 3/4 an hour lecture, then 3/4 an hour practical. That's my standard model. I've left it slightly vague in there, but this isn't an hour and a half lecture. This isn't an hour and a half lecture. Neither is this. It's a combined lecture and practical. So are there any final questions? If I can, if there is something which I haven't mentioned here and you would like to hear about, then please let me know in the chat. We can talk about it one-to-one, or I might have some of the slides on it. But for the moment now, we'll take a break and we'll